Okay, Professor Masoumi, I think you can start your talk. You have 25 minutes for your talk and 5 minutes for questions. Please go ahead.
Thank you very much. Good morning to all, or good afternoon, or good evening. It depends on the place you are in. My talk is about the light of the moon, Ibn al-Haytham, or in his Latinized version, Al-Haytham and Galileo. I begin by a book which has been published in 1647. The book is called Selenographia Sue Lune Descriptio, and its author is Johannes Hevelius. I think that most of you know Hevelius for his discovery of several new constellations which are invisible to the naked eye, and he discovered them by the use of his telescope. His telescope was on the roof of his house in Danzig or Gdansk in the present-day Poland. The results of his observations of the moon are represented in this book, Selenographia, or Sue Lune Descriptio, Selenographia, or the description of the moon. It was published in 1647, 5 years after the death of Galileo, and almost 6 centuries after the death of Ibn al-Haytham. And his aim in this book was to rectify and to complete Galileo's description of the surface of the moon as reported in Galileo's The Starry Messenger, his famous book. Why I am interested in is the title page of this book, which is an allegorical illustration. In this illustration, you see two men standing. The man at the left is Al-Haytham. His name is written here under his figure, Al-Haytham. And the man on the right is Galileo. His name is written here, Galileo. Beneath the figure of Al-Haytham, you see a schematic drawing of something which resembles to a brain. And beneath this drawing, there is a word, a Latin word, ratione, that is reason. Beneath Galileo's figure, you see his name and an eye, and under the eye, you see the word senso, that is sense. Don't go ahead. Like many drawings of this kind in the books of that period, this drawing has an allegorical meaning. Its aim is perhaps to show that astronomy can progress only by a combination of reasoning and observation. Nevertheless, in the book itself, there is nothing about Al-Haytham's contribution to our knowledge of the moon. The author mentions Al-Haytham or Ibn al-Haytham in several occasions for his work on optics, on reflection, and on refraction. A few words about Al-Haytham. He lived at the second half of the 10th century and the first half of the 11th century. Mostly he lived in Cairo in Egypt, and he's known above all for his book, which is called the Book of Optics, or Optics, to be short. This book was written in about the year 1000 and had a great influence on the later development of optics in Europe, as is shown in the dates of cite here. The book was translated into Latin in about 1200. In about 1270, a Polish monk named Vitello published a book named Perspectiva, which is the Latin word for optics. And this book was a kind of commentary on the optics of al-Haytham. The optics was also translated into Italian in the 14th century, which was not a very common event because at that time, Italian was not a language usually used for science. After the invention of printing in 1572, a man called Reisner published these books together, that is the Latin translation of al-Haytham's optics, together with Vitello's Perspectiva. And in 1604, Kepler, the famous Kepler, published a book which is called Ad Vitellionem Paralipomena, which is one of the main texts of modern optics. And as its name is shown, it was some remarks about the book of Vitello, which himself was a kind of commentary on Ibn al-Haytham optics. And the other person of our talk, Galileo, he published his the dialogue concerning the two chief world systems in 1632. Another text of modern optics, Descartes' Dioptrique, was published on 1637, and as I said before, the Hevelius' Selenographia was published in 1647. As for the optics of Ibn al-Haytham, I have given a list of some of his main achievements in the Book of Optics. His starting point is that he created a really new science of light. That is, he put aside the prevalent idea of the existence of visual rays which were emitted from the eye and were the means by which we see the things. He said, he proposed that we can explain all phenomena related to vision only by the use of light rays, and we don't need this concept of visual rays. And in this program, he investigated all the domains of optics, the rectilinear propagation of the light, for its reflection, its refraction, and one of the new things of Ibn al-Haytham's optics is that to the main categories of the propagation of light, that is its reflection and its refraction, he added a new concept, which is the concept of the secondary light. When a beam or a ray of light falls upon an opaque body, a body which is neither polished nor transparent, this body itself becomes a secondary source of light. That is, light is emitted from all points of this body in every possible direction. And you can imagine that a secondary light, a second can fall upon a third body, and the third body becomes itself a source of light, so that there is an infinite increase in the sources of light in the world. With these new ideas, he investigated some problems which had never been subject to a scientific examination before Ibn al-Haytham's new optics. These problems, some of these problems are related to the moon. He has written a treatise on the light of the moon, another treatise on the face we see on the moon. And it is about this first treatise on the light of the moon which I am going to talk. On the problem of the light of the moon, there were two theses. The first thesis was known at least from the 5th century BC, and it said that moon is not a luminous body. It receives its lights from the sun. And this thesis is found everywhere, even in philosophical, in astronomical, in optical writings. The second thesis, which was also accepted by almost everyone, was that the moon is a polished body which reflects the light of the sun. That is, the moon is something of a celestial mirror. In the treatise named The Light of the Moon, Al-Haytham shows that the moon emits the lights received from the sun like an opaque earthly body. That is, he shows that it does not reflect the light received the sun toward our eyes. To show that the moon is a secondary source of light, Ibn Haytham devises an experimental apparatus which is shown here. I am not going to into the detail of this question. Anyway, for the lack of time, this is the device by which Ibn Haytham shows that the light we receive from the moon comes from every point of light and every direction. In the second part of his treatise, Ibn Haytham tries to demonstrate, and in fact demonstrates, that moon is not a convex spherical mirror, that it does not reflect the light received from the sun in the technical sense of the word reflection. His demonstration is a mathematical or a geometrical demonstration, which is based on two ideas. The first idea is the formation of image in a convex spherical mirror. The second idea is that of the distances between the sun, the moon, and the earth. Here, this diagram shows the formation of the image of the point A in the spherical mirror, which is here. How the problem is that for the observer situated at point B, the light emitted from the point A falls upon the mirror and is reflected to the point B, so that the angles of incidence A, M, L, and the of reflection, that is B, M, K, are equal. so the image of point A is point A prime. The important thing in Ibn al-Haytham's demonstration is the equality of these angles and the fact that the incident ray AM, the reflected ray BM, and the tangent at the surface of the mirror lie on the same plane. As for the distances of the sun and the moon to the earth, Ibn al-Haytham used the distances given in the books on astronomy. Here, M is the moon, E is the sun, earth, and S is the sun. For the distance of the unit of measurement in all cosmological dimensions in ancient astronomy was the diameter of the earth. So Ibn al-Haytham gives the figure 50d for MA, that is the distance between the moon and the earth is 50 times the diameter of the earth, which is not bad at all. It is the mean distance. It is because the distance between the moon and the earth is very variable in ancient astronomy. As for the distance between the sun and the earth, Ibn al-Haytham gives a figure about 1,200, which is too small. It is only 1/400 of the real value. And the reason lies in the measurement of angles and the intervention of the tangent function in this measurement, which I lie beyond the scope of this talk. This figure shows how Ibn al-Haytham demonstrates that light is not reflected of the surface of the moon. This circle here is the solar disk. This sphere here is the moon, and Z is the eye of the observer. Using the laws of the reflection of light, Ibn al-Haytham shows that if the moon was a spherical convex mirror, the part of the moon on which solar rays were reflected would have been very small and indeed even invisible. This arc KL gives the width of the part of the moon on which solar rays are reflected. By a similar argument, he calculates the length of this part, and he shows that this part of the moon which can send back to us the solar rays through reflection is in fact very small and indeed invisible. So much for Ibn al-Haytham. As for Galileo, this is the picture of Galileo, and this is the front page of his great book, one of his two main books, Dialogue Concerning the Two Chief World Systems, Ptolemaic and Copernican. This is almost the standard translation. This dialogue goes on between three persons. One is the mouthpiece of Galileo, a very learned man, which is called Salviati. The other one is Simplicius, which is an Orthodox Aristotelian. He believes firmly in the Aristotelian Ptolemaic worldview. And there is a third person, Sagredo, which is some kind of intermediary between these two persons. And most of the time he comes into the dialogue in favor of Salviati, that is in favor of Galileo. I pass over this part, which is the problem of the shape of the moon. Anyway, Galileo, in a part of this dialogue, Galileo shows that the moon, despite the existence of mountains and valleys on the surface of the moon, which were discovered by Galileo himself, the overall figure of the moon is spheric. And this is something which was accepted by everyone, including Simplicio. But Simplicio accepted this idea by purely philosophical arguments, whereas Galileo chose to demonstrate the sphericity of the moon by observable phenomena. And there is a very close similarity between this part of the Galileo's book and the part dedicated to the problem of the shape of the moon in Ibn al-Haytham treatise on the light of the moon. As for the light of the moon itself, Galileo bases his argument on the difference which exists between reflection on plane mirrors and on spherical mirrors. I pass over the details and the quotations of his work, and the result of his idea, of his discussion is shown in these two figures. Here, this line represents a plane mirror. These are light rays which were all parallel, and when they hit the mirror, they are reflected in the same direction. That is, the reflected light rays are also parallel. Whereas this one, the other figure, is a spherical mirror. Two parallel rays which fall upon this mirror are reflected in two totally different directions. That is, the first ray is reflected in this direction, the second ray is reflected in this direction. The first ray reaches the eye, the observer, whereas the second ray is lost in the space. Now, if we compare the two scientists, the two men, we see some similarities and some differences between their approaches. As I said before, the arguments they present for the sphericity of this, for the spherical shape of the moon are almost the same. Both base their argument for the rejection of the idea of reflection on the surface of the moon on the difference which exists between reflection on plane mirrors and on convex mirrors. And I have written here concave, which is a fault, an error. And both arrive at the same conclusion. The light emitted by the moon, that is the light, the moon emits the lights received from the sun in the same way that an opaque everybody emits the light. That is, the light is emitted of all points on the surface of the moon and all possible direction. And we can conclude that the main optical ideas used by Galileo are those already expressed in Ibn al-Haytham's optics. This is not very strange given the great popularity of Ibn al-Haytham's book in the Europe of that time. As for the differences, the main difference is that Galileo had a telescope. He had already seen the surface of moon with its mountains and valleys, and he firmly believed by this observation that the moon is a body much like the earth, whereas al-Haytham could only draw upon his optical knowledge and what was known at the time of the sizes and distances of the sun, the moon, and the earth. The other difference is that the method of al-Haytham is quantitative. He calculates by geometrical arguments and by using the sizes and distances that the part of the moon which could reflect the solar rays is very small compared to the surface of the moon which we see in the sky. The argument of Galileo is qualitative. Instead of the moon himself, he uses a spherical and a plane mirror. Whether in fact he has made this experiment is a subject of thought. And the last difference is that for al-Haytham, the concept of secondary light is an irreducible concept. That is, it is something different from reflection and different from refraction. Whereas for Galileo, the secondary light, which is the result, that is the light we receive from the moon, is the result of a great multitude of reflections produced on different parts of an opaque body. And to conclude, as far as we know, the treatise of al-Haytham on the light of the moon was never translated into Latin or in any other European language before the 20th century. So Galileo did not naturally know the results already obtained by al-Haytham. But in fact, he reproduces in a different way this result, but in this reproduction, he draws heavily upon the optical principles already formulated by al-Haytham. The main achievement of Galileo in his dialogue, or at least in parts of his dialogue, is considered to be his idea that the earth and the heavens are made of the same stuff as that of the earth. It was a great step toward the rejection of the cosmological dualism, which was dominant throughout the antiquity and a great part of the Middle Ages. I hope to have shown that al-Haytham's research on the light was in the same direction. That is, it showed that at least among the heavenly bodies, the moon resembles deeply to the earth. Thank you very much for listening. Now, if there are any questions, I don't know if...
Thank you, Mr. Professor Masoumi Hamedani, for your nice talk. If any questions,
May I just add that this principle by al-Haytham later on is called Huygens principle, that every point of the body receiving the light starts to emit in all directions, a spherical wave.
Yes.
It's very similar.
Dr. Masoumi.
Anyway, the Huygens, in his wave light, extended to in this idea on any point of a wave front, that is, any point of a wave front is a source of light which sends light in all directions.
Okay, Professor Subhuti, please, if you have questions.
Good morning, Dr. Masoumi. I'm Subhuti.
Good morning. Yes, good morning.
Very nice lecture. Very, very nice.
Nice to hear you. Nice to hear you.
Why don't you translate this into Persian and let the wider population of Iranians know this beautiful work that you're presenting?
Thank you. I try to do it. In fact, I
Very
have
beautiful.
I have translated all the Ibn al-Haytham's treatises into French, and it will be published. I hope it will be published soon as part of a book.
Okay, French people have good translators. Why don't you present your work in Farsi, in Persian, and so that the wider faction of the society will know it? None of us know. None of us knew these things.
The main reason is the lack of time or the many different occupations I have.
I recommend.
but I try to do it. Thank you very much.
I recommend you send your translation to Nameye Farhangistan Ulum,
Yes.
the letters of the Academy of Sciences of Iran.
Thank you.
They have a monthly. They have a
yes, I know it.
Quarterly. They have a quarterly publication.
Yes, I know it.
I recommend to send it to them.
I try to do it. Thank you.
Thank you very much. Very beautiful. Beautiful lecture.
Thank you.
May I also ask a question?
Yes, please.
First of all, thank you for your talk, Dr. Masoumi. My question is about the role of Greek philosophers such as Euclid and Ptolemy on Ibn Haytham's work. Because in his Kitab al-Manazir, or Book of Optics, he mentions both of them by name in his first book, yes, I believe.
In fact, he knew as everybody, knew Euclid's optics very well, but he went very far there than Euclid. He knew the Ptolemy's optics also, and somehow the organization of his book is somehow related to the organization of the Ptolemy's optics, but the main difference was that Ptolemy's optics was based on the idea of visual flux and visual rays, whereas Ibn al-Haytham's main aim was to put aside this concept of visual rays and to do everything only by light rays. And some chapters of Ibn al-Haytham's book resemble to chapters of the existing text of Ptolemy's optics, because you know that Greek text of Ptolemy's optics is lost. The Arabic translation of this Greek text is also lost, and all we have today is a Latin translation made from the Arabic translation. So our knowledge is very second-hand, and this Ptolemy's optics as it exists today lacks certain chapters which were very important, especially a part of the fifth chapter, which was on the refraction of the light and on the atmospheric refraction. Anyhow, Ibn al-Haytham knew well these two books, but he tried to go beyond these two works. Thank you.
Thank you for your answer.
Okay, any other comments or questions? Okay.
Well, congratulations for this very nice presentation.
Yes.
Thank you very much.
Many thanks again from the speaker, and let's clap for him. And let's go to the next talk. The next talk is by Professor Richard Kerner from Sorbonne University, and he is well known for his works in mathematical physics, but now today he is going to talk about astronomy in Islamic world. Richard, you have 25 minutes for your talk and 5 minutes for questions. Please go ahead.
Thank you very much. Thank you for invitation. I thank Soroush and Remo, and now I have prepared a very long talk, so I will skip some parts of it, but you'll have the entire version. Soroush will put it on the website of the conference. So my talk is about astronomy in the Islamic world, and it's a very vast, of course, topic. And I start with the sources that Islamic science took its sources on both sides of geographical spread, namely in Greek scientific tradition, which was conserved in Byzantine and Hellenistic Egypt, both Christianized since many centuries, and in Indian mathematical and astronomical traditions. The Greeks owned much of astronomical knowledge to the earlier Babylonian and Egyptian civilization. However, they enriched and extended them in unprecedented proportions. So now I just show a little bit of Indian mathematics and astronomy. The earliest acquaintance of Islamic world with mathematics and astronomy was due to Indian and Persian influence. From India, the Arabs took the decimal system with numerals and zero, which we use today. The main Indian mathematical text by Brahmagupta dates from just before Islam, from 6th century, and it was later translated into Arabic. It contained, among others, the idea of negative numbers, their algebraical properties. They were called depths, in opposition to positive numbers called fortunes. Not only algebraical addition was defined, but also the multiplication with well-known rules, including the fact that the product of two negative numbers is positive. And all this, of course, was
Richard, excuse me, please. Would you please make the screen full screen? It is somewhat little where we can.
Full screen. Okay.
Okay.
Is it better now?
It's better. Thank you. Thank you.
Good. So this is Aryabhata, the father of Indian mathematics. He was the greatest mathematician and astronomer in ancient India. And his major work was Aryabhatiya. It consists of spherical trigonometry, quadratic equations, algebra, plane trigonometry, sums of power series, and arithmetic. And it all was, of course, included in Arabic mathematical tradition later on. Now, the three pillars of Greek science, which were adopted by Arabs and Islamic polymaths, were Aristotle for physics and all natural sciences, Euclid for geometry, and Ptolemy for astronomy. Their major works were translated, copied, edited, and commented for centuries. And Aristotle would assume the title of the first teacher, vouching for all the intellectual heritage of the Greeks, viewed as systematic knowledge compatible with Muslim worldview. Together with Aristotle's own works, the Arabs translated an equally great amount of commentaries tracing back to the late antiquity, particularly to the school of Alexandria, and some of Plato's texts were translated at the same time. Now I'll skip some things and we'll start with the Golden Age, and to show what was the state of the world, of the old world, at the dawn of Islam. It's important to see that the Rome was the western part of Rome was completely in shambles, whereas the eastern part, speaking Greek, and which conserved most of the Greek science and everything, was still alive, and it was the Byzantine Empire. And another empire which was comparable in size and in population was Persian Empire, Sassanid dynasty. So this is the state of the world that Arabs inherited when they started the expansion. So in the midst of 7th century, as you know, a new religion was proclaimed by Muhammad. In Arabia, it was derived from Jewish and Christian traditions, simplifying them and professing with great conviction the uniqueness of God. This was an important revolution because it replaced the tribal principle by a more general religious and social unity. And at the same time, while Europe entered the era of Dark Ages, lasting because of barbaric invasions and the collapse of Roman Empire. So the Arabs have conquered vast territories, creating a buoyant Islamic civilization which spread from Moorish Spain in the west to western North Africa, through Egypt and Mesopotamia, touching India and even the most western parts of China. This is the map that shows the spread during a few centuries, it is absolutely unparalleled, as you see. Well, you know the history, of course, and I just want to say that the only precedent of so rapid expansion was the Hellenistic empire built by Alexander the Great. So like ancient Greek and like in the Roman Empire, Arabic language became universal among Islamic scholars, with Persian and Turkish as subsidiary sometimes. But the most important thing was that there was one language uniting all scientists.
Sorry, Richard, we lost your presentation.
I don't know why. It's I see it.
Yes,
We can't
but
see your slides.
No.
you can see.
Please start.
No, we cannot.
No, you can share again.
Is it okay?
Yes.
Okay.
Oh, yes.
Yeah. So,
Great.
of course, during that time of splendor, sciences flourished, especially mathematics, chemistry, called alchemy or alchemy, and astronomy. A number of scientific terms of Arabic origin are in use in Western science until today and known to everybody. It's enough to cite a few like algebra, algorithm, zenith, azimuth, nadir, alcohol, alkali, and many others. So now I go to cite the most important scientists in Arabic and Islamic world. So the first was Al-Farabi, known under the name of Al-Farabius. He spent most of his time in Baghdad. A prolific writer, he authored comments on Platonic and Aristotelian philosophy, and plenty of works on physics, alchemy, psychology, astronomy, and music. His authority was so great that in Islamic world that he was often called the second teacher after Aristotle, who was the first teacher. And his comments paved the way to his philosophical synthesis by Ibn Sina, Avicenna, and Ibn Rushd, Averroes. And in late years, he moved to Damascus. Then Avicenna or Ibn Sina, renowned physician and philosopher, called the third teacher. His most appreciated work was the Canon of Medicine, a manual of medical science in many volumes, which became the authority for European doctors after it was translated in Latin. Among his lasting contributions was the drug testing method and the discovery of infections of tuberculosis. He is also called not only the third teacher, but also Persian Galen, because of this fantastic contribution to medicine. And here is, it's interesting to know that the political turmoil was very characteristic of these times. And for example, Avicenna had to, he finished in Isfahan, and here's showing his him at the court of governor of Isfahan when he came after a fantastic peripheral. You see, from he was born here in Central Asia, and then came to Nyasa. He was in Tush and Samarkand, and finally finished his days in Isfahan. Now, Al-Biruni, famous geographer and astronomer who improved Aristotle's estimate of Earth's circumference. He also wrote a geographic description of India, a source of historical, botanical, and zoological facts, unfortunately never translated into Latin before modern times. Then, of course, the great Averroes, Ibn Rushd, considered as one of the greatest Muslim scientists. He was born in Andalusia, in Moorish Spain. And that was at the time of Almoravid dynasty. And during his life, he passed to Almohads, and that was the great, very bad for science, because Almohads, the Almohad Caliph Al-Mansur, prohibited practicing music, poetry, and philosophy. Averroes was accused of heresy and banished from Cordoba, then from Andalusia to Morocco, and he never returned back. Nevertheless, his influence was the greatest among all Arab and Muslim scientists. His influence in Europe was the greatest. He was studied, the writings were studied in Padua, Salamanca, Oxford, and Sorbonne. and influenced many of European scholars, so much that they were called the Averroists, and somehow 100 years after Averroes' death, the St. Thomas refuted most of his ideas. But there were some extremely modern ideas. One of the questions he posed was whether our thinking is entirely comes from our inside or is somehow imprinted from outside by God. So that was the great discussion among the scholars at that time. And it is, I think it is actual even now, whether our thinking is really independent or formed by publicity, for example. So here's Averroes in Cordoba. And now I turn to mathematics. One of the most often repeated claims is that Muslims invented algebra. This is largely true, even if initially they took sources in ancient Greek and Indian mathematics. But the very word algebra, which comes from Arabic al-Jabr and means restoring or putting together, was coined by Persian mathematician and astronomer Al-Farabi, who lived in Baghdad, and in his treatise in Algebra wa al-Mukabala. I'm not fluent in Arabic, so maybe I pronounce it wrongly, but it means science of putting parts together and balancing. In modern algebraical terms, the first word referred to the possibility of replacing terms from one side of an equation to another. Like we write now, for example, most of our equations are something equals 0. So that was a very great step forward and made by Al-Khwarizmi. The name comes from Khwarezm. It is in Uzbekistan. And in Latinized version, it is known now as the name algorithm, which means any prescription of algebraic actions. Here's Al-Khwarizmi statue, and on the right you have postal stamp with Al-Khwarizmi emitted in Soviet times in Russia. So now astronomy. Of course, during the Golden Age, astronomy was one of the most important sciences. Of course, it was very tightly mixed with astrology, because people at that time everywhere, they believed in the influence that planets can exert on human behavior and what happens on Earth. But of course, the religion was also very important, because the exact timing of 5 obligatory prayers a day, beginning and the end of fast during the month of Ramadan, linked to the first and last crescent of moon, establishing times of Islamic holidays, all that created the need for astronomical observations. Mosques had to be oriented towards Mecca in the Arabian Peninsula, and so should be positioned the Muslim during his prayer. This alone needed improved geographical and astronomical knowledge. And finally, vast territories of Islam with flourishing terrestrial and maritime trade made necessary the emergence of practical astronomy, improving observational devices like sextants, astrolabiums, to be used on land or in the open sea. Here, and of course, the main centers were Baghdad, Cairo, and also Toledo and Damascus. These instruments invented then included celestial globes, quadrants, sextants, armillary spheres. And of course, the most sophisticated of all was astrolabe. Here there is an astrolabium from Toledo, 11th century, and right armillary sphere from Damascus on 12th century. You see how sophisticated they were. And astrolabium was a kind of, in a sense, it was an analogous computer. You could compute things and positions of, and on the other side, you had an alidade that you could see the objects, celestial objects. And I just, to show how big was influence of Arabic astronomy in Europe, you have names of many of most important stars are Arabic: Aldebaran, Algol, Altair, Betelgeuse, Deneb, Tukre, Polmachaut, and many, many others. This is just for fun. This is Islamic astronomers working. This is a picture from Turkish book from 15th century. Now, the Arab astronomers translated Ptolemy, this syntaxis, which was called Almagest because it was opus magnum. And the most eminent Muslim astronomers include Al-Battani, Al-Sufi, Al-Biruni, Al-Bitruji, Ibn Yunus, Al-Tushi, and Al-Shatir. So I will just make a small presentation of every one of them. So Al-Khwarizmi, whom we discussed already as a great mathematician, but he was also a great astronomer. His important strides in astronomy and geography include the measurement of the length of a degree of a meridian in the plane of Sinjar, improving Aristotle's evaluation of Earth, and a world map based on the geography of Ptolemy, providing more accurate coordinates of approximately 2,400 sites in the known world. And they were contained in his book, Kitab Surat al-Ard, the image of the Earth. Now, another of Khwarizmi's treatise was made into Western canon, was a compilation of astronomical tables, including table of signs, and was translated into Latin. And he also produced two treatises on sundial, astrolabe, and one on Jewish calendar. And he was translated, the algebra was translated in the 12th century, in the beginning of 12th century, by an Englishman, Robert of Chester. Now, Al-Battani, he was known in Europe as Albatenius, was the author of Sabian tables. It's called Al-Zij al-Saba, work which had great impact on his Muslim and Christian successors. His improved tables of the orbits of the sun and moon comprise his discovery that the direction of the sun's eccentric, as recorded by Ptolemy, was changing. This in modern astronomy means the Earth's line of upsides is slowly moving. He also worked on the timing of new moons, the length of the solar and sidereal year, the prediction of eclipses, and the phenomenon of parallax. Here is Al-Battani, called the second Ptolemy. Then he was also a pioneer in the world of trigonometry. Now, the Sabian tables were translated, and they were more accurate than Ptolemy's. In his De Revolutionibus, Copernicus was to refer Al-Battani's calculations no fewer than 23 times. Now, the Abd al-Rahman al-Sufi made several observations of the obliquity of the ecliptic and motion of the sun, or the length of the solar year. He became renowned for his observation and description of the stars, position, their brightness and color, setting his results constellation by constellation. For each constellation, he provided two drawings, one from the outside of celestial globe and another from the inside, the very inside. He also wrote on astrolabium, finding numerous additional uses for it, including one's location, measuring distances, and heights. It was almost like GPS now. Now, Ibn Yunus, the Egyptian astronomer, his work in French edition was centuries later an inspiration for Laplace, and in his obliquity of ecliptic and inequality for Jupiter and Saturn. Ibn Yunus made observations for nearly 30 years, using, amongst other, a large astrolabe in Italy, and he was also known that he improved the Hipparchus data about the precession. Hipparchus estimated precession as 1 degree per 100 years. And Yunus made observations, and he said that it is 1 degree in 70 years, which is much closer to the reality. Here is Ibn Yunus and one page of his book, Al-Zij. Al-Biruni claimed that Earth rotated around its own axis. He also discussed the possibility that Earth could rotate around the sun, but he rejected it. And in addition, the late century Abu al-Wafa and Prince Abu Mansur stated and proved theorems of plane and spherical geometry that could be applied by astronomers. Al-Biruni was our master pupil. He produced a vast amount of high-quality work and was one of masters in applying of these theorems to astronomy and mathematical geography. Here is Al-Biruni and Iranian stamp commemorating his work. There was Al-Farabi, one of Caliph al-Mamun's astronomers. He wrote on Astrolabe, and his most famous book on cosmography contains 30 chapters, including a description of the inhabited part of Earth, the distances of heaven bodies from Earth and their sizes, as well as other phenomena. Now, Arzakali, or Arzachel, prepared the Toledan tables and was also a renowned instrument maker who constructed a more sophisticated astrolabe, Sapiha, with the treatise how to use it. And then Jabir ibn Afla was the first to design a portable celestial sphere to measure and explain the movements. He is especially noted for his work on spherical trigonometry. Al-Bitruji's work, Kitab al-Haya, was translated by the Sicilian-based Michael Scott and bore considerable influence thereafter. Now, Nur ad-Din al-Bitruji, known as Alpetragius, lived in Moorish Spain, and he was probably a disciple of astronomy to fire. Unfortunately, although he was very good at calculus, but it could not improve better Ptolemy Almagest. It improved it in the sense that there were many more epicycles. Al-Bitruji rejected the notion of equant and the notion of non-concentric, how it is called, one is equant, another is eccentricity. Everything has to be centered in Earth, and only the multiplication of epicycles made the things stronger. It was in a way it was just like Fourier analysis. Now I skip to medieval observatories. At the time of decline, I should, sorry, in astronomy, I skipped, I should also speak about the greatest, Al-Tushi, Al-Tushi was the last great astronomer of the Golden Age. Of Persian origin, he studied in his native town Tush, then nearby Nishapur, educated in philosophy. And he acquired the reputation of an outstanding scholar and became a member of Ismaili court invited by Abd al-Rahman. And what is interesting is that after, here's Al-Tushi and the stamp in Iran, after Hulagu conquest of Baghdad, he named Al-Tushi a great court astronomer. So in this sense, even the Mongols were aware of importance of astronomy. So this is Hulagu, who made Maraga his capital, and there was this great observatory, which I will discuss if I'm given 5 minutes time more. This is Al-Tushi. He was famous for the Al-Tushi couple. He proved, in some sense, he disproved the Aristotelian postulate that all motions in sky have to be circular. He proved that with certain circular motions, which is called Al-Tushi couple, and used by Copernicus later on, you can reproduce straight motion along a straight line. And finally, I'll skip Ibn al-Shatir. This was the last prominent astronomer in Damascus. And he was known for his book, The Final Quest Concerning Rectification Principles, with new lunar, solar, and planetary models. Here is Ibn al-Shatir and one of his sons. And if I have 1 minute, I will discuss the 2 great observatories of Islamic world. One was the Maraga Observatory in Iran. And now I think it is it in Iran or rather in Uzbekistan? And no, it's in Iran. I know that there are some parts of it which are still visible, but most of it was completely destroyed. This is one of the rare circles in Maraga Observatory that is still visible. And there was an anonymous treatise in Persian, Al-Ghazan, on the observational instruments during the reign of Ghazan Khan, the seventh Ilkhan of Ilkhanid dynasty of Iran. And the most of our sources about Maraga Observatory comes from this text, from this anonymous book, which is reproduced here. And the astronomical equivalent is fantastic because there was a 40-meter large radius, a mural quadrant, a solstitial armilla, triquetum, many fantastic, unparalleled until the invention of telescope or the European science, unparalleled astronomical devices. These are some of them. This is one of the simplest instruments. You see, it is like this. It can show you, this is called alidadi, you can observe something and then you get directly the x, the sine and cosine of the angle and the azimuth. You can have two angles, azimuthal angle and the altitude. This is another instrument in Maraga, that was in Maraga, also very simple. It's you see, it can be turned azimutally and it can be directed towards some celestial object and you can measure angles directly. This is a little bit more sophisticated, also in Maraga. And you can see the details on the presentation which Surush will put on the website. And now the last great astronomer was Ulugh. He was born in northern Iran at the end of 14th century. He was the oldest son of Shahram, one of Tamerlan's sons. And he was given Transoxania, which is now Uzbekistan, Central Asia, to be a ruler of it. And Ulugh succeeded Shahram, but survived only 2 years as independent ruler before being overthrown and beheaded by his own son in 1449. It's a tragic. Here's Ulugh and Samarkand Madrasa, which is extremely rich and can be visited even today. Here's a commemorial sculpture for showing Ulugh and his students, pupils, and the quadrants, an enormous quadrant, 40 meters of radius. He's remembered for his extraordinary achievements in astronomy. He was the greatest astronomer of his century, not only in Islamic world, but in the world. And the greatest mural sextant was made by Ulugh. He measured obliquity of the ecliptic, and well, I just skipped this. And he was later he was translated into Latin and given to European scientists in in the 17th century, the masterpiece Chronology. So this is and his achievements could be were unsurpassed until Tycho Brahe's more than a century later. And this is my book. I just take advantage to make a little publicity. I wrote a book on it is called Our Celestial Clockwork, and of course what I'm speaking, what I told you here is contained in this book, and many other things until the 18th century from Babylon, Egypt. And so thank you for your attention. It's I'm sorry for being long.
Okay, thank you very much, Professor Kerner, for your very nice talk. Okay, if any questions or comments?
May I ask a question?
Yes, please, Mr. Professor.
Okay, first of all, thank you very much for your amazing talk on Persian astronomy. I just wanted to add something and then ask your perspective on that. I believe that Omar Khayyam also played an important role in astronomy, math, and geometry. For example, he devised the Jalali calendar, which is still in use today, and is the most accurate calendar, even more accurate than the Georgian calendar, which is used in Europe. What do you think about his role that he played in Persian astronomy?
Well, it's hard to tell because there are so many contributions. I'm sorry that I didn't mention him because I think I mentioned him in the book. The problem is probably with Omar Khayyam that his notoriety is because of poetry. He's so much appreciated as poet that it completely occludes his astronomical and scientific achievements. This is the situation because he was in Europe. He was extremely appreciated as a great poet and translated, and probably this because of this it somehow occultates his. It was certainly very important.
Yeah, thank you very much.
Thank you for of course, thank you for mentioning him. He deserves, as many others, that I did not mention, but it is a very rich topic. So you cannot, in half an hour, you cannot tell everything, of course.
Okay. Any other questions?
Yes, definitely. The name of Omar Khayyam is really very important, almost to take as an example of a period of serene civilization, which could be a starting point again today as an example.
Yeah, the problem, if I can comment, I mean that with all these fantastic achievements, the Islamic astronomy, in a sense, is a part of, it is the last part of it makes one block with ancient, with Greek astronomy, with Indian astronomy. You can call it antiquity. So it is the latest part of antiquity and not the first part of modernity. The modern approach started in Europe and with Copernicus. And this was the real revolution.
Richard, can you hear me? May I ask a question?
Yes, please.
So thank you for the very nice talk. Actually, after your presentation and the previous one, you both mentioned about the important role of that period of the history in the astronomy.
Yes.
But what's your idea? Why the people always in the standard literature skip all of this effort and start from 70th century? And you already said that you mentioned all of this in your book, but what's your idea about skipping that important period of the history of astronomy in the standard literatures?
It is not only the astronomy. There's a lot of things. Well, there is a very interesting book by Bernard Lewis. He is an American specialist of Islamic history, Islamic world. And the book is entitled, What Went Wrong? I think I can show it to you. What went wrong?
So what's the quote?
The question he asks is why, with such enormous effort, when it collapsed. But he gives many things. For example, one thing was, for example, in when the Turks conquered Constantinople, they started very well. They kept some scientific people and so. But later on, for example, the printing was prohibited in Ottoman Empire until the mid 18th century. The printing of books. Can you imagine? This is something. There was kind of the same thing happened in Spain when Almohad they prohibited everything. The people, the philosopher has to flee. And probably one of the reasons was the political instability. The things that take Ulugh, for example. He was his legacy was destroyed not by Europeans but by his son. This is some kind. I think this is the reason, and so it collapsed by itself, probably mostly because of political instability. There is one data, for example, that the number of dynasties in Islamic world as compared with Christian world is 10 times as big, the number of dynasties, because they changed very, very often, too often. And so probably the political instability was one of the reasons.
I see your point. Thank you so much.
Thank you.
Okay. Any other comments or questions? Okay, let's thank the speaker again, and thank you very much, Professor Kerner, for your nice talk. Okay, thank you, everybody. We have a break, and we will join after 20 minutes.
10 minutes, sorry, 10 minutes. After 10 minutes, we will come back. I will write here.
Thank you, everybody.